Now, right? All right, we're going to continue and probably we're going to finish this chapter today. Okay. So we were talking about the equation. You had energy of activation there, frequency factor, temperature, everything, right? So let's see a little bit in detail how the frequency factor is going to affect the rate of the reaction. Okay? So how are you going to control the speed of reaction? So how some reaction going to be faster, some going to be lower, right? So some going to take a little bit more time and other faster, right? So you can see this, you can say picture. So different possibilities of collision. Okay. So our reaction is this. So you're gonna have the reaction between, say, alcohol, and then you have the water. So you are just dissolving alcohol in water. Okay. So this is going to be the equilibrium reaction. So suppose you have the alkoxide. So this, you can say RO minus for shortcut, the same thing. R going to be the alkyl group there. You have ethyl in this example, right? CH3, CH2 is C2H5. That's the ethyl. Okay? And then you have the oxygen with minus charge. So now it's going to take the hydrogen and this is going to be the product you have. Okay? So hydrogen addition to the alkoxide ion. Okay? So now to have this reaction, it is obvious that two reacting species you have, they're going to collide, right? So you have different direction for the collision in different orientation. Okay? So suppose in the first case, you have the oxide ion exposed. So molecule comes this way, right? And then you have the water molecule on the other side. Suppose you have the oxygen of water is exposed there. So two oxygen are going to collide when you have the collision. That's one possibility. Okay? So do you think this is going to give the product? No. So why? Focus on the bond you're going to make. So this is the bond you're going to make. So you're going to make the bond between the hydrogen of water. So I'm going to draw like this way. So this is the focus over here, hydrogen. And then you're going to have the alkoxide, say O minus, right? Ethyl there. So you're going to make the bond between these two, O and H. That's the one you're going to make. Okay? So for this collision, this one, it does not involve these two atomic centers in the collision. So that will not give the product. Okay? See the other one. You have the hydrogen of water orientate towards the second molecule, and the hydrogen of the alkoxide ion. So now you have the hydrogen of that exposed, so two hydrogens are going to collide when they have the collision. Right? This is also not the right orientation. So this will not also give the product. Okay? That will not going to give the product. That will not give the product. Alright? So what's going to be the right one? So the hydrogen of water to that of oxygen of alkoxide when they collide, then yes, you're going to have the product there. Right, so you're going to have the bond between the oxygen of alkoxide with the hydrogen of water, then you're going to have the product. Okay, so this is called the proper orientation or the correct orientation. So out of many possibilities, you're going to have very few the correct orientation that only going to give the product. So in that equation, you have the orientation factor A, right? So this is the fraction of correct orientation. If you have, say, 10 possible orientations and one correct, 1 over 10 gonna be that A. Okay? So that depends on how big the molecule is, how many atoms you have in the molecule. So all gonna affect that. Okay? So if you have the small molecule, you're gonna have the orientation factor larger because you're gonna have few atoms there. You have few possibilities. You're gonna have one out of these few possibilities there. If you have larger molecule, you're gonna have many atoms there. More possible orientations you have, the fraction gonna be smaller in this case, right? So that's how it's gonna affect. So the next gonna be the activation energy. We see that. So how are you gonna define that? So if you have any energy profile like this, right? So you're gonna have something like this one, right? So this is gonna be the reactant, and then the top you're gonna be the transition state, right? Transition state. So whatever you have the energy difference between these two, that's the energy of activation, EA. Okay? So this is the easy way to define it. The energy difference between the transition state and the reactant, not product. Okay, so product can be up and down depending on the exothermic reaction or endothermic reaction. You're going to have the fluctuation of the energy of the product. So you're going to take the reference of the reactant. So energy difference between the reactant and the transition state, that gap is always energy of activation. Okay, so you're going to define that way. So if you want to show the structure in the transition state, the approach is like this. So you're going to draw something like this one. Right? So transition state is going to involve these short-lived species. This is going to be very unstable. It doesn't exist for a long time. It's going to be instantaneous. Okay? Either the transition state does not form, so the system will not have energy to go there. That may be the case. If you have, then it's going to give the product right away. Okay? So forming the transition state is the difficult task. It's going to involve energy. Once it forms, then it's going to change to either product or reactant, depending on the reaction conditions you have. Okay? So that's why for the transition state, you're going to involve both reactant molecules and the possible product you're going to form from there. That means you're going to have the bond partially breaking and then partially making. Okay, so bond making going to give the product, breaking going to break the reactant molecule towards the product, right? So here in the same example, you're going to make the bond between oxygen and hydrogen, right? That's the target. So you're gonna see over here. So this is the partially bond formation. So they're gonna give the product, right? That gives product. You have. And then you're gonna have the OH, that of water over here, that bond you have, it has to be broken to give the product, right? So it is not completely broken, but it is breaking. So these two gonna involve simultaneous process. So gonna happen at the same time. So this gonna be partially broken, and the other one is partially formed, and then finally you're gonna have the product, right? So you're gonna show this way. So you're gonna write the dotted line for the partially making bond and breaking bond. You're gonna show both bond between the molecules. Normally it is written with the square bracket like that, because this is kind of complex. If you recall, Lewis acid-base complex, this is like that, right? So this is the complex. It involves both type of molecules there. And then this is gonna be the sign for the transition state. Sometimes you're gonna call the activation complex for that, the same name, right? So you're also gonna call that activation complex. This is the other name, sometimes you see in the book. So this is transition state, okay? So now, after this, if you are worried about the entropy, of course you're going to have the less entropy there, right? Because two molecules, like acting as a one molecule, you're going to have the less number there. So you can think like a less degree of disorderedness. Or you can say the more ordered form if you compare with just the reactant molecule itself. So in the reactant side, you're going to have the individual molecules. You can count 1, 2 for that, right? So you're going to have the 1, you're going to have 1. So total is going to be 2 particles there. But from transition state, you have only 1. Both kind of like partially combined, right? So you're going to have less entropy for transition state if you compare with the reactants. Okay? Alright, so now you can show the same thing over here. So this is the reactants you have, right? So this is transition state, you have the top over here, and then you're going to have the product over here. Right? So now you can show the energy of activation. So that's going to be the energy of reactant you have. You're going to take from there up to the transition state. So that difference is EA, energy of activation. Okay? Of course, you're going to have the product. So in this case, what do you think? Delta G that we saw in the previous class. So delta G gonna be a plus or minus? What do you think?
The minus.
Minus, right? So it is below the reactant energy. So you have minus over here. So it is below how much? This much. You have that difference negative. If you are exactly on the reactant line, you're going to have delta G 0. You're going to have the same energy of product than that of reactant. Okay? If you have above this, say for example, let me write with the other color. So from here you're going to come like that, like this. So now product gonna have more energy than the reactant. So delta G gonna be plus. If you have like that, delta G gonna be positive over here. right? So product minus reactant, you have product larger value. So larger minus smaller value going to be the positive value, right? So that's how you can, just by seeing the energy profile, you can say whether it is favorable reaction or not. That is whether you're going to have the negative delta G or not. Okay? So this is one way of saying that. So by the way, before I go, what is this? Exothermic reaction. It releases heat, right? Mm-hmm. So what's going to be the value of delta G for that?
So G is negative.
Negative, right? So as is, if I don't do any modification over here, this reaction is exothermic reaction. So whatever energy difference you have, reactant and product, this is negative. So it is releasing from the system to outside. So if you perform this reaction in a beaker, and if you touch the beaker surface, you're going to feel heat. That means the energy is coming out from the mixture in the beaker. Okay? So if you have any diagram, something like blue line over here, like I modified it, right? So what is going to be the reaction type? Endothermic reaction. If you have the product energy higher than the reactant, then whatever difference you have, that you have to supply there to have the product. That means the mixer is going to absorb whatever you supply energy there, say heat energy, you're going to heat the mixer, right? So it is endothermic. So the endothermic going to absorb energy to itself from outside. Exothermic going to give the energy outside, not it's going to absorb it. Okay. So now we have one postulate. So based on the same energy diagram you have, just by looking at the diagram, we can guess the structure of the transition state. So this is based on that. Okay, we call Hammond postulate for that. That's the name. So why are we going to learn this? If somebody asks, all right, you're going to have the transition state structure, you can draw by the dotted line for the bond backing and backing, right? But if you're going to compare the structure of the transition state, right? Or you can say whether you're going to have the bond between the forming one gonna be more completion or the other way, right? So this theory is gonna say about that. Okay. In other words, in which direction the transition state is gonna resemble the structure, to the right with the product or to the left with the reactant. Okay. You're gonna just see the transition state, that, and then you're going to see whether it is close to reactant or close to the product in terms of the energy. Or you can say whether you're going to have the energy gap between the reactant and the transition state. So I'm going to say this one over here. So this gap with the reactant, right? So this is going to be always energy of activation you have. Or whether you have the gap here, transition state and the product. So which one is closer of these two?
Reactant.
So, or you can say which one is smaller. Okay? So the smaller in energy difference is going to be closer. So in this particular diagram, the transition state is closer to the reactant. then to the product. Okay? If you have this, then the structure of this complex is going to be similar to the reactant, not to the product. Okay? You can have the other case, like say for example, you have this structure over here. So I'm gonna make something like this. So now the gap you have with the product, this gap, so this is gonna be closer to that of the reactant, right? So now the structure is gonna be closer to the product, not to the reactant. So endothermic and exothermic reaction gonna have the different transition state in terms of the strength of a bond breaking and making. Okay? So that's the Hammond postulate. So after this, we're gonna see a little bit about the rate law expression. So we are not doing any derivation over here, just the qualitative treatment, okay? So this equation should be very familiar, right? So rate of the reaction gonna be equal to K A to the power A and B to the power B, right? So does it familiar? So then come 2, right? So one thing you're gonna know over here is order of reaction. If you write N for that, A plus B, okay? So this is the order of reaction, which is N over there. If you have only one reactant, you're gonna have the single number there, so it's gonna be simple. If you have the mixture of reactants, then you're gonna take the sum of the power for each reacting species you have. Okay? So here, let's say you have A and B, 2 reactants you have, and then you're gonna have order equals A plus B. So A gonna be the order with respect to reactant A, and then B gonna be the order with respect to reactant B. Okay? So now the thing you need to be very clear is, let's say small a and small b are the coefficients in the balance reaction, right? So do you think order gonna be the sum of the coefficients you have in the balanced chemical reaction or not? Never. So A and B, the sum, that is N, this is gonna be always from the experiment. Sometimes it can be, right? It may happen to have similar to the coefficient you have, but not all the time. So if you see the table over here, this is from the experiment, right? So you're gonna vary the concentration and then measure the rate of the reaction, and then you're gonna solve that, and then you're gonna calculate the order from there. So we're gonna find out that way from the experiment. That's why it is experimental quantity. So you cannot write whatever you have the coefficient in the equation as the power of the rate law expression. Okay? It may be a little bit confused, like looks similar to the equilibrium concentration terms over here, but not. It is different. Okay? So now let's say one reaction, you have the first order with respect to A and B, so you're gonna have 1, 1 over there, so N gonna be 1 plus 1. So overall gonna be the second order reaction, but if you take the order with respect to one reactant, it's gonna be first order. Okay? So you can see in the experiment, say for example, this is the starting concentration you have control. So you're gonna start 0.1 concentration, right? So for this expression, if you double A, so which is 0.2, right? This is 2 times the initial concentration, right? So if you write the rate, so Kr, so for A, I'm going to write 2 times A, right? So 2A, so we're going to write the power 1 over here. And then you have the same concentration B, so I'm going to write B as is. We don't have any change on that. So if I solve, what's going to be that? So 2 going to come out, 2 times Kr, A and B, right? So double than the initial rate we have. If you double the concentration of the reactant, you have a rate going to be doubled. Okay, if you triple the concentration, rate going to be tripled. So if you have the first order, it's going to go like that. Alright, so you can see that in the table. So if you double, you're going to have the double rate than before. If you double another reactant, keeping the first same as before, you don't have change over here for trial 2. So you are making a double for another reactant. So still you have 2 times the rate, right? And then if you double both, so you're going to double the first reactant concentration, double the second one. So what's going to be the effect? So 2 going to become out from one reactant, another 2 from another reactant. 2 times 2 going to be 4. So you have 4 times the initial reactant, right? So that's the effect of concentration. Okay? Any question on that? Good. All right. So what about the second order? If you want to see the transition state for the same type of reaction, so what's going to be the transition state? This one. Okay. So for that, you're going to have a little bit competition there. So out of 2 reactants, which one is going to control the transition state? The slower one going to control the transition state, right? So whether breaking of this or forming of this, so you have 2 steps over there. If you have the simultaneous, this is another kind of reaction. So we're going to see, we're going to go from simple one. So the slower going to control the reaction, right? So, for example, water, if you have the hydrolysis as an example, you're going to have a lot of water over there. So the water concentration virtually has nothing to do with that. So the other going to control the reaction, right? So this one you can take virtually out over there, right? And then you're going to have the other 2 effectors, like something like this one. So this does not have any contribution there. So you're going to have the first order, even if you have the 2 molecules. Okay? So don't be confused there. So being 2 reactant molecules may not be the second order overall reaction for all the time, because it is the experimental quantity. So we're going to see how it's going to behave experimentally. We're going to measure the rate, solve the equation, and then we're going to know what order the reaction is. That's how we're going to do. Yep.
Is this sort of the concept we check into where we choose the slowest step?
Yes.
Wow.
Yes. So slowest step going to be the rate determining step, right? Or you can think this way. So you have the 1, 2, 3 like that, right? So sometimes you're going to have this series of transition states there. So this is for the one reactant, this is for the second reactant, this is for the third reactant, like that. So out of this, what has the highest barrier you have? That's going to be the slowest. You can call this rate determining state, right? RDS circle. So they're going to control it. So that's how we're going to do it, right? Any question on that? Alright. So by the way, so this thing over here, we're going to write RDS for the shortcut. Okay, rate determining state. Alright, so now with that, let's see a few reactions, and then we're going to compare reaction speeds with those concepts. Okay? So halogenation of alkane. So we know alkane, right? What is alkane? So hydrocarbon, right? So what type of hydrocarbon you have? If you have CnH2n plus 2, that's the alkane you have, right? Other word, you can say if you have hydrocarbon in which you have the 4 bonds with each and every carbon you have there. Not double, not triple, right? So completely saturated carbon. If you have that, it is alkane. Okay? So here, if you take ethane for example, so you have the 4 bonds there. So it is saturated by hydrogen, right? That's the alkane, ethane. So now the title says halogenation of this. So what that means? So you are adding halogen to alkane. Halogen addition to alkane. Alright? So you're going to form the new compound. So what that going to be? So you're going to remove hydrogens from there. You are taking this hydrogen out, for example, and then let's say chlorine, for example. So chlorine molecule, you're going to put chlorine in place of that. You're going to have Cl there. You're going to replace hydrogen by Cl. That's the halogen addition. So this is called the haloalkane or alkyl halide. Okay, that's the name. So alkyl halide, so you're going to call that. That's the compound you're going to form. Right? So you have the alkane. So methane is going to be the simplest alkane you have. So this is methane. So you already know the name, right? If you see the table, you're going to see that. Methane, you have 1 carbon atom. If you have 2, going to be ethane. 3, going to be propane. 4, going to be butane, right? You can take any alkane. So, plus you have the halogen. And then you're going to give this, okay? So now, if you see over here, so you're going to hear the reaction, okay? So you have the alkane, halogen, you have the mixer, you're going to heat that, you're going to have the product. This is the alkyl halide, so methyl halide, right? So you have 1 carbon there, so methyl, so you have the chlorine for halogen, chloride. So that's going to be the product you have of the halide, okay? So now let's see in detail for this reaction. Okay? So what are the bonds broken and what are the bonds formed over here? So you have the CH. So out of these, so how many CH bond you have? 4, right? So all are identical. So this gonna be breaking, okay? Breaking. And then you have another breaking over here, chlorine, Cl and Cl bond you have, you're gonna break that too. So it involves 2 bonds breaking, right? And then what is the bond formation there? You have the carbon and chlorine. That's the making you have. So you're going to have the 2 bonds breaking over there, 1 bond forming. Okay? If you compare the major reactant, of course you're going to have H and Cl forming over there, right? So now, if you want to know the how this bond gonna break and the product gonna form, we're gonna call the mechanism for that. That's the name. The detailed step-by-step description of the formation of the product you have from the reactant, from the starting. That's the mechanism. That's the name for that, right? So, it's gonna come from experiment, of course. Okay? So how are you gonna form the product? So the name of the mechanism is gonna be radical mechanism. Okay? That's the name. Because at the beginning, the radical is gonna form, and then it's gonna propagate for the reaction. They're going to induce the reaction step there. Okay? So how the radical going to form? So we're going to see over here first. Okay? So this chlorine, so you have a heat over there. It doesn't do itself. You're going to heat that. So you're going to break the bond. When you break, then what's going to be the product? Radical. That's the one. Because you have 1 electron on chlorine. So you have 2 over here, 2 electrons forming the bond. So you're going to break that, and then you're going to divide electrons equally, 1 each. So you're going to have the radical. So chlorine radical there, right? So this is also called the homolytic fission, right? Or homolytic breaking, right? So why homolytic? 1 each equally. Right, so you're going to distribute the bonded electrons equally between the atoms that form the bond. Okay? So you have the radical, so that's why the name comes from there. Radical mechanism. Okay, so now you're going to start reaction. Okay? So this is the radical you have just formed. And then you have the methane. So this is CH4, just writing different way, same molecule, right? So it is showing the bond over here, gonna make it easier, that's why you can write this way. So 1 bond HC, and then other 3 bonds are not shown, so you have 3 hydrogens remaining there, right? So now, what's gonna happen? So this is gonna take the hydrogen out from methane, and then you're going to have the radical, another radical. So now methyl radical, okay? This is methyl radical, right? And then this radical is going to react again with another chlorine molecule, and then you're going to produce the equivalent radical again, right? So This is the formation of radical from another radical you have. So, the name for that is propagation. So, the first was initiation. You have the chlorine radical formation at the beginning, that's the initiation. And then now the second going to be the propagation. So now if you compare these two, what is the difference? So sometimes in your exam, like out of these 3 or 4 steps, which one is initiation step? Which one is propagation step? So it can be asked that way, right? So what is the difference between initiation and the propagation? You have both over here. So what difference you see there? So compare the left side to the right side. Okay? So for the first initiation, what you have on the left side? There's the molecule, right? Neutral molecule. You don't have any charge there. Do you? No, right? What do you have on the right side over here? Radical. So, in any reaction, any step, if you have molecule on the left side, and then they're going to give the radical on the right side, this is initiation all the time. That's the way you can identify, right? So formation of radical from the neutral molecule. That's the initiation. So now if you compare that to the propagation, you see the difference. So let's see what you have on the left side. Radical, right? What do you have on the right side? Radical. If you have radical on both sides, that's the propagation. So one radical is going to give the another radical. So that's why it is propagation. It's like a chain reaction. It's going to continue until it doesn't find anything to give the radical. So it's going to be chain reaction type. So it's going to continue, all the reacting molecules are done. Okay? That's the propagation. Now the third step is going to be the termination. So now the name, as the name suggested, we're going to have some clue. So probably you will not have any radical on the right. Right? So you're going to see on the left side, you have the radical over here. What do you have on the right side? Molecule, right? So no radical on the right side. So you have on the left side, but not on the right side. So these 3 are all termination steps. Why? You have the radical on the left side, but you have the molecule on the right side. So now if you compare this with the initiation step, what is the difference? Just the reverse, right? So the termination is the reverse of initiation. So for the initiation, you're going to have the molecule on the left side. For the termination, you're going to have the molecule on the right side. Right? So now you can distinguish chain reaction types produced by radical. So what is initiation? What is propagation? What is termination? Right? So for this halogenation reaction, this is the mechanism. That's how it's gonna proceed until all reactants gonna change to the product. Right? So first you're gonna have the halogen radical. It can be bromine, can be chlorine, or fluorine iodine. So iodine is gonna be too slow, fluorine is gonna be too fast. So we're gonna deal with chlorine and bromine for that reason. So first you're gonna have the chloride or bromide radical, right? And then they're gonna react with the alkyl halide to have the haloalkane, right? No, to have the radical. And then the radical gonna react with another radical like alkyl bromide to other radical, and then you're gonna have the molecule, right? So that's how you're gonna have product, right? So this radical with another, you're gonna have the molecule. Alright, so let me go back. So now, if you see this one, so one thing you're gonna compare now is the stability. Right? So for the methyl, you don't need to see this one. But if you have the different alkyl radical, let's say for example, this one, the simple one, and then you're gonna have the CS3 and then hydrogen, this one, this is also radical, and then you're gonna have 2 CS3 and 1 hydrogen, this is also the one, and then you're gonna have CS3, 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 and then this one. So this is same as this one, okay? This is same as this. So just writing different way. Okay? So now the question is, if you have all alkyl radical, out of these, which one gonna be more stable? Which one gonna be less stable? So, what do you think? The answer is over here. Right? So now the question is, which one is 3 degree? Which one is 2 degree? Which is 1 degree? And then which is methyl? So methyl is gonna come over here. So CH3, that gonna come over here. Okay? That's the last one. So you know 1 degree alkane, 2 degree alkane, 3 degree alkane carbon. If you see the carbon center, you can define what degree is that carbon is in alkane. So you can do the same thing over here. So see the carbon you have, and then you're gonna define 1 degree or 2 degree or 3 degree. So here you're gonna see the carbon that has the radical in it, 1 electron in it. Pick that carbon. Okay? So now, which one gonna be 3 degree? So the carbon that has 3 CC bond, you have, that's the 3 degree, right? So which one? This one, right? This is 3 degree. Because you have 3 carbon-carbon bond there. So which of these are one we are looking for? This one, this one, this one. So you have 3, and it's 3 degree. What about the other one? You have 1 cc, so 2, that's 2 degree. You have only 1 carbon there, that's 1 degree. So it doesn't have any carbon, that's just the methyl radical. That's the simplest possible alkyl radical you're gonna have. Okay? So now, as this says, the 3 degree is gonna be more stable than 2 degree, than 1 degree. So why do we think that case? So these alkyl groups you have, they are considered the electron donating group. If you have any electron deficiency on the next carbon to the CH3 unit, that's gonna give a little bit of electron to that side, so it's gonna make more stable. Okay? So you have 3 alkyl, you're gonna give more, gonna be more stable. So the more alkyl group you have nearby the charged carbon, more stable is gonna be that one. Okay? So that's the way you're gonna define, right? We're gonna stop over here.